Hey guys, and welcome back to another Unreal Engine tutorial. Today we're using Unreal Engine 5, which is the new version of Unreal Engine. You can find it in your Epic launcher and download the early access and open it up. You will find something similar to this. Just like before, you can add features and content packs with like your template assets, so you can get your mannequin and the third-person player pawn, that kind of thing. But we're not going to need any of that today. Today we're making a material. We're going to make like a kind of an accurate LCD screen material. Pretty customizable. We're going to be using an actual sort of pixel-based sort of light logic here. And well, on that, I made you guys a little care package. We got this little pixel texture, which we'll use to make our color appear. And I just took a screenshot and squared up this image from the Unreal Tournament 4 alpha. Rest in peace. Okay. So a little bit about how like LCD screens work. We have sort of a lattice of little squares on your screen called pixels. And each pixel is comprised of these three cells, each one that shines out red, green, or blue light. The combination of all three of these shining up at the same time results in white light. And obviously if they're all blackened out, then you would get black. Using these three colors and varying degrees of each, we can we can show basically any color that we want on an LCD screen. And we'll see a little bit more about how exactly that happens as we go on. So let's just right click here in our content browser and make ourselves a new material. And we'll call it LCD screen underscore matte. All right, now let's open that bad boy up and grab our textures, and we'll just drag them onto our material graph so they appear as texture samples. And I'll snap this up here so we have a bit more space. Okay, cool. Now we can start building out our logic. So we're not going to need to do anything to the actual material settings here. We're just going to leave it as default. It's all going to be fine. But okay, let's think about what we need to do. Well, for one, we need to manipulate the UVs of our pixel texture. So instead of having one spread out across the entire image, we have as many as we need. So you might have seen me do this a lot in my Unreal Engine 4 tutorials. We hold a U and click, you'll get texture coordinates, which just return, in fact, if I set this to a plane, it'd be a little easier to see, which is going to return the coordinate locations of any particular position on the texture. And if we multiply these values, it's going to scale up the texture coordinates, resulting in many instances of this texture appearing in the same space. And we can see exactly how that works with this texture coordinates node. If we hold in M and click for a multiply node, and then we hold in S and click for a scalar parameter, which we will call UV multi, and we'll set this to 1 for the time being, plug these two into this multiply node, then this multiply into the UVs input of our texture sample, and then the RGB of our texture sample into base color. We can see that with our texture coordinates multiplied by 1, we get the pixel across the entire surface. But if we bump this up to say 10, now we get 10. If we bump it up to 50, now there's 50. We can do as many as we want, like 2,000 if you wanted to. And we can kind of see the effect working here a little bit. 2,000 is probably a little bit high. Let's go down to say 1,000. We'll halve that. But you see, when we multiply these pixels way out, the resulting color that we get is this sort of pleasing middle gray. But we zoom in carefully, we can start to see the pixels. Pretty cool effect. And I find it very interesting that this still works, in Unreal when it's a real world effect. Anyway, that's just me. I'm interested by these things. Okay, so let's not set that to 1,000. We'll set it to something. Oh, the other thing to keep in mind is that it needs to be. It needs to fit on your screen. So if you're not using a plane with the power of 2 sizing, then you'll have to set some other tricky calculations here. In fact, we'll go through that very quickly right now. So if I take out this scalar, duplicate it, let's say we call this one, oh, come on. Let's call that one 2, just so that they're different. And we come out into an append. So we go append vector, and then plug this append into this multiplier. The result with these two set like this is going to be the same as if we were to put 2,000 in this multiply here. It's now just multiplying X and Y by 1,000 each. But if we drop this down, say we drop this down to like 64 and 64, just so that we can see some pixels on screen there. And then grab the, I think this will be the X one because it's on top, it's in the A. If we crank this up, you can see it's stretching, or in this case, it's compressing the pixels. We've set it something lower, even lower. You can see how this is affecting it. So if you do have a non-square plane to use, just this little setup here will allow you to fit that properly. Okay, so let's just lose these for the time being. We'll just plug this straight into this multiply. The value that we'll go for, something like 256, I think should be fine. And you can even see, I don't know if this will come through on the recording, but that kind of wavy, like fractal almost kind of effect on the screen, which I quite like. So we'll keep that as is, and we'll move forward. Sorry that took so long, little sidebar, but now we're ready to proceed. So here is our texture with our image. This is the image that will be displayed using our pixels. So we're just going to right click this, convert it to a parameter, and we'll call this image. This is so that we can edit this as an option in the material instance, if we choose to instance this material. And we're also going to hold in 3 and click to get a color. We'll right click this, convert it to a parameter and call it tint. Because we can also make some final adjustment by manipulating this tint value. And I'm just going to set that to white now so we can still see it in the preview. And we're going to need 3 more colors. So just hold in 3 and click the graph. We need one that's going to be red. So if you want to do this manually, you can see the channels here. We just need 1 in R, then 0 in G and B. Same with the others. Well, not same, but 0 in R, 1 in G, and 0 in B. And lastly, 0 in R and G, and a 1 in B. This gets us the pure RGB values that we need to make this material work. Now, the next step is to divide up our texture, our pixel texture, into its red, green, and blue channels, which, I mean, is done here with these RG and B outputs. We hold in lerp 3 times. We'll need 3. 1 for red, 1 for green, and 1 for blue. And for each of these outputs, we're just going to use them as the alpha. Now, the way that linear interpolate nodes work is that we take in an alpha, and using the alpha values, it's going to return the difference between A and B. So, for example, in fact, we can see it if I just preview, if I right-click the lerp node and preview it, you can see that it is white now because it's defaulting to, or it's not white, it's middle gray, because you can see at the top here, the alpha value is at 0.5, so it's halfway between 0 and 1, which results in gray. But if I change, say, constant A to 0.5, actually, I'll keep it at 0, but if I change the alpha to 0, we have black. If I change the alpha to 1, we have pure white. So the constant, the alpha is going to be the middle point. Well, it's going to be applied to A and B and return values based on that. And in this case, we're going to be using the R channel. So if I just plug this in, 0, 1, yep, and we zoom in, you can see we only have the red pixel currently active. And if I start previewing this lerp, it's difficult to see. In fact, we can, if I make so the bottom value like a 0.1, no, it's not going to quite work. No, that's okay though. Yeah, well, just for the sake, if we do the blue, you can see it's now the right-hand pixel. So we're isolating each of these pixels, and we're going to be multiplying it by, our tint value, but first by our image. We need the channels out of the image. So the red channel has to be lerping with the red of our red channel lerp here. So our image has appeared now, but this is just the red channel, and it's going to be, they're all going to be grayscale outputs that we're just going to overlay over the top of one another to recreate our original image, but with these pixels here. So same, just like before, let's do green. Have a look at the green channel. So it looks slightly different to the red channel. And the blue channel, start previewing that. It looks a little bit different again, depending on how much blue is in this image. And there's quite a lot up the top here, but apparently not a lot down low. So we'll stop previewing that and we'll move on to the next step. And the next step will just be to multiply these colors in with the tint values. So let's grab these colors here. We need to hold in M and click for multiply, and we'll need 3 multipliers. So our colors here will go into A of each multiply, red, green, and blue respectively. And then for the tint, we need the red into the red multiplier, green into the green multiplier, and blue into the blue multiplier. Starting to get a little bit tricky to see. We'll just disconnect that base color. We're not going to need that really. And I'll move this image sort of over here. All right, I think we're ready to move forward. So the next bit is to combine our tint with our image. So if I just pull this to the side a little bit, we'll need another multiplier each for the red, green, and blue channels. And then we'll just plug in the result of our tint multiplier into A, and then of our lerp into B. So the multiplier for the red channel goes into a multiplier with the lerp from the red channel, and same with green, the multiplier into A, the lerp into B, and with blue, the multiplier into A and the lerp into B. Next thing, we can just add these back together to create our final image. So we hold in A and click, we'll get an add node, and it doesn't necessarily matter which order we do this in. We just need to add each of these things back together. So we'll plug in the result of the red multiplier into an add into the A, well, a second add into the B of our first add, and then the remaining two multipliers into this second add here. I hope I've explained that well. So this pretty much finishes the initial kind of result. We can plug this straight into base color, and then we can see the kind of result that we've got, and we can zoom in here and see how things are interacting with the pixels. Pretty cool. I mean, if you had a lower res picture or an unfiltered picture with just the right amount of actual resolution, you can even get that grid effect around each pixel. For the purposes of this video, though, we're just going to be recreating the effect and not worrying too much about it. But if you wanted to take the time and take the sort of more careful planning with it, then certainly up to you. Depends on what your project depends on. Okay, now let's move on to some sort of flavor, do the last few things involved in an LCD screen. So for one thing, LCD screens are lit. They have a backlight. So let's hold in M and click for a multiplier, hold in S and click for another scalar, and this will be our glow crank. And we'll set our glow crank just to 1 for the time being. Plug this into B of our multiplier, and we'll plug this into our add. And before we plug that into emissive, let's do something else. So the other thing about backlit LCD screens is that they do have a flicker. It's a bit like a fluorescent light flicker. If you were to like film a TV in slow motion, you might see that flicker for yourself. So let me do that. So to achieve this effect, let's grab a time node, and this is a little bit like event tick. It's just going to return the time, and we can perform calculations on it as we go. Hold in S and click to get a scalar. Call this one flicker rate, and we'll set it to something fairly high, 200. Should do it at least to start. So let's just multiply these together. So by multiplying the time by a value, we're sort of accelerating how frequently it's going to be returning data for us. From this multiply, let's get a sine wave, which is just a fluctuating grayscale value that's going to go up and down, or down to 0, up to 1, and back. And we use this little multiplication here to determine how quickly. So out of our sine wave, we'll come into a divide, and we'll just divide this by 2, just straight up division. And then we'll add 1 back to our final value. And this, when we preview, gets us a flickering effect. I do apologize if there are any light sensitive people in my audience. There we go. Turn that off. We can control this flicker rate though. If we set this to 1, you can see a slower kind of effect. So this is what the sine wave with our calculations results in. And this would be perfect for our screen flicker. So I'm going to pump this back up to 200. And where were we? Next, we'll clamp these values so it's not too bright and not too dark as we go. And to do that, we use a clamp. And a clamp is just going to take in any value that we want and return it between a minimum and a maximum value. So it's not going to exceed these two values either up or down. So we need 2 more scalars. We need the flicker low bound. That's our minimum. And we also need the flicker high bound. All right, and our high bound, we'll say something like 0.9, and our low bound, something like 0.7. So we don't need to go all the way to black. We don't need to come up all the way to white. We just need to show that flicker, you know? Okay, so let's grab a multiply node. You can hold an M and click, or Control W to duplicate, and just hook these guys up. There we go, and now this multiply can go straight into emissive. All right, brilliant. Now, the last thing is the shine on the screen. We need, actually, is that even, I don't know if I've done this quite right. Nope, I've missed the high bound, 0.9. There we go. All right. That was a little bit dodgy. Let's see what's going on over here. Yeah, there's some flicker there. We may have to adjust these values in the instance. It's pretty subtle. Not a problem. You can kind of see if we zoom out. Yeah, that's not bad. Okay, the last thing is the shine. The shine on the face of the screen, because they always have a kind of glossy, clear-coated overlay. And to do that, we will use a Fresnel function, which is a fairly cheap way to kind of achieve depth or some nice sort of reflections in your materials. Today, we're going to be using it for our roughness values. So as you can see, with default roughness, there's really not much going on. It doesn't look very smooth or shiny. So let's take our Fresnel function here out of this output here. We'll go straight into a multiply, and we're just going to multiply by -1. I know that you can come in with a boolean here, and not here. Where is it? In the invert Fresnel, but I've always just preferred using a multiply just out of the output. Makes no difference. The next thing is to lerp. So we need to lerp this alpha here, and instead of going 0 to 1, we need to go 1 to 0. And then we'll just multiply it by a factor. So I'll also duplicate our glow crank, hook this up into the A, and rename this. We'll call it rough multi. And it'll be set at a fairly low value, 0.15. And we'll just plug this into roughness. Now, if we right-click this multiply and start previewing, we can see what our roughness is going to look like. So you can see when you're on oblique angles, there's going to be a bit more reflection than if you were not. So that's as intended. In fact, if we switch it to a sphere, yeah, so you can see kind of where we're trying to apply roughness, basically everywhere except this sort of middle space, but in a kind of diffused, soft kind of result. And you can see there's the specular highlight. Okay, so this basically finishes off the effect. So to zoom out here, and we'll have another look at it. We have this little sine wave piece of maths down the bottom here for the flicker on screen. We have this little piece here with the Fresnel function to control roughness. We have our glow, our brightness, like our backlight in the screen here with a simple multiply and a glow crank. And all the magic is happening in this chunk of code over here, which is just multiplying the UV coordinates of our pixel texture. I wonder if there's a better place I can put this. It doesn't really matter. So yeah, we multiply the UVs of our pixel texture. We multiply it by a tint color, which isolates each channel. And then we lerp back our pixel colors through the image in order to determine our final result. So let's hit save, and then we'll go check it out in the editor. So back over here, let's head up to place actors. We just need a sphere, not a sphere, a plane. So hit geometry, not geometry, shapes. And we'll get a plane up in here. Details, let's crank it up a little bit. We'll make it, hit this padlock, so this is all uniform. Make it 10 by 10. Sit this upright. It's facing the light, give or take. And then move it up. All right, so let's make an instance of our material. Just right-click and create instance, and then drag it onto our plane. Guess what's currently sideways. I think that's due to the default UV orientation of the built-in plane. Doesn't matter. We can see here that, well, our LCD is working. This purple that we're seeing could be because there might be, I don't know, a few more red and blue pixels in the pixel texture, but we can affect that if we open up our instance, pull this down here, and turn on all of our scalars. We can take this control back. So where's our tint? To counteract the purple, we'll need some yellow. Then we can try and approach a more sort of neutral color. Neutralizes that purple effect. Cool. And then we can see our reflection. We can see the flicker, and when we zoom in, we can see the pixels. And you can even see, so if we look over here at this orange, you can see, as I mentioned before, about sort of the nature of how LCD screens work. Here's a good spot here, because this is like orange, right? This is the bright orange color. And as we can see, we see mostly red, a little bit of green, but very, very little blue, because green and red creates yellows and oranges, but blue isn't involved. So the blue pixels are all dark, while the red ones are all lit up. So it's kind of accurate with real LCD screens in that regard. But with that said, I think that's all for this video. So thank you guys for watching this far. I hope you really enjoyed it. And I hope you liked this Unreal Engine 5 tutorial. I'm kind of torn as to whether to sort of make the jump straight to UE5 or to do sort of a mix of UE5 and UE4, or just not bother with UE5 at all and just see what happens in the next, the next few months in terms of releases and that kind of thing. Let me know your thoughts down in the comments below, or better yet, as always, the easiest way to get in touch with me directly is via Discord. So jump in the server. There'll be a link to it below. If you like my work, if you like the channel, definitely feel free to support. There'll be a Gumroad link and a PayPal donation link also in the description below. Thanks again, guys. I'll catch you in the next one. Cheers.